Here we go. Here we go. Okay. So I have opened Grasshopper, and now I have to open the Grasshopper file, which is this one. Yeah. When you try to open a file and you don't have a plugin, this menu, this window pop-ups, okay? It's just saying that I am missing one plugin that is called Elefront. It's super useful. I recommend you all of you to install it. Since you already know how to install plugins, because we did it last class, it's a really cool one. I mean, it's very useful. Elefront and I always forget the name. Lunchbox are the two, from my point of view, the two main plugins that Grasshopper has. So, this was our last class. Okay, I'm going to do a small recap, okay? Because I know that usually Christmas are tough. Okay, so here is our plot, and we were doing this thing, right, of dividing the different floor plans with different patterns, and then deleting elements on those floor plans, and then extruding them. Okay, this was our last solution. By the way, guys, you are going to receive feedback next week about your previous intermediate submission. Okay. So yeah, you will receive information about how you're doing and all these things. Sorry for being late, but the problem is that our team assistant was sick for a long time, and I don't have access to the list of students. So to put the grades, I need to do it with the list, to check that all of you are properly registered. If somebody is not registered, I will contact you, okay? Because in this list, I can see if you are registered or not. The problem is that I don't have access to this list, and they have to provide me. And yeah, took a long time, much more than expected. But sorry for this. But I hope that next week you will have your grade on the here, okay, on the Ilias. By the way, you don't know it yet, but you have a Christmas present or holiday present or is extra content, okay, that somebody you can have a look of it about Grasshopper. If you're interested about Grasshopper, if you like Grasshopper and you want to go deep on it, you can have a look of these resources. Some of them are PDFs. For example, this one. Let me open it. Those are Grasshopper examples. They start from scratch, okay? Some of them have some time. You will see that the graphics are like a bit old, but it's not so old. It's from less than 10 years, but things haven't changed that much, to be honest. And you can follow those. It's a start from the beginning. So a lot of stuff here, you have already seen it with me. For example, the longest list algorithm behavior of Grasshopper, all these things. But there are some exercises. They speak also about trees. You can see from where I get the drawing. And yeah, they have really, let me see, blah, 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 blah. Where are the examples? I think at the end, this is BB. Also about coding in Grasshopper. Well, one second. I recommend you specifically Model Lab. This one I recommend all of you to have a look if you're interested. It's not necessary for the course, but it is very beneficial. This one is really good. Hello Grasshopper, anatomy of a Grasshopper definition. Here you can follow exercises which are really interesting. You can do this is done with attractor points, okay? And yeah, you can follow those examples. You have the definitions here. They explain step by step how to do them. This one is super simple. It's just like this. And yeah, you can have a look of the exercises that you have here. They work with colors that we don't have time in this course to work with those colors. And okay, have a look if you're interested and keep on expanding your knowledge about computational design. So once I have said that, let's go with our grasshopper definition. For today, give me 1 second. I'm going to open here another one. One moment. I'm going to put you here. If you have any questions about what we have done till now, don't worry, we can see it after the course, okay? Give me 1 second, guys. I'm trying to open here to guide me another definition, and then I can have a look of the steps. 1 second. Here we go. Okay. So here we are. From where does this thing come from? We are going to work today, instead of with the geometry that we produced the other day, we are going to work with the buildings that comes from where are those buildings? Give me a second. So we are going to work here. Okay, I'm gonna put here a panel for me to don't get lost about it. And yep, we are going to work with the geometry. This is the problem, you know, when you don't have a plugin in Grasshopper, things are displayed like this. The EF data description is a component that comes from another plugin, and I didn't install it. I mean, I installed it. The problem is that this plugin is out of it. Okay, so this comes from this geometry, from class 3 geometry that we use to generate our base buildings. Okay, we have here 3 buildings that we generate, for example, with these rectangles. Okay, but without any modifications on it. Okay, you can use this one, or I mean this one, because we did it with the curves. Okay, we did it with those 3 curves, and we generate our buildings here. I am going to use this one. Okay, I'm gonna put the comments in the chat somewhere here. Yep, I can have a look. So we are going to use these buildings, or not this one, not the gradient building, only the class number 3 shows geometry buildings, this one. I'm gonna put a geometry component here. Good. And then I'm going to do one thing. When I had to move geometry from, how can I expand here the chat? Like this, nice. When I have to move one geometry from one class to another one, which is far, 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 far away, like for today, we are going to work here. What I should do, guys, is I'm going to put a geometry component, okay? And I am going to do right mouse button and write, for example, I don't know, base building, or base building class 03. Okay, and then click on the bucket. Okay, I'm going to copy this one, and I am going to connect this one with this one. Seems a bit redundant, right? Seems that. Annalena, you mute me?
Sorry, I wanted to let someone in, but the person just vanished, and then I pressed your button.
Okay, okay, no worries. It's good, just to know, because suddenly I was muted and I was like, hey, what is going on? It's good, no problem. So as I was saying, I put another geometry component, and what I do is right mouse button, wire display, hidden. Okay, I'm going to, I think that this we already show it, right? We already saw this. To hide, they are connected, but the wire is not displayed. You have this sign here that seems like a Wi-Fi. For what I'm doing this, I'm grabbing this component and bring it to here, to our class of today. Okay, and from here we can start working. Okay, what are we going to do? We are going to do something that is called a Voronoi 3D. We are going to do two definitions today. One of them is going to be called Voronoi. Okay, you're going to learn what are Voronoids. And another one is called, I don't know how we can call this. Like, it's kind of voxels. I always call it voxel, but it's not exactly this, but well, let's going to call it voxels, okay? That I will show you also what is a voxel. Okay, so we have for today those two definitions. Let's going to start with the Voronoi. But what is Voronoi? Let me show you. The best definition of Voronoi, honestly, you can find it in Voronoi. You can find it in Wikipedia. This is the best source. Basically, and super shortly speaking, is a partition of a plane into regions close to each of given set of objects. You can read all of this. Basically, what a Voronoi is dividing an area into points. You have to provide points. That's the first thing. And the distance, the area generated between those 3 points, for example, this is generated in the middle of this line. This line is generated in the middle of the line that connects those 2 points. This line is generated in the middle of the line that connects those 2 points. Okay, so following this procedure, calculated midpoints of line that connects points, the Voronoi diagram is generated. Okay, it's like this. All this math cell you have here works like this. Grasshopper by default, they have Voronoi. They have Voronoi and Voronoi 3D. Okay, Voronoi works in a plane. Okay, and Voronoi 3D works in a 3D. Okay, in a 3D environment, doing exactly the same thing, but in a 3D context. Voronoi are widely used in architecture. I mean, there was a time that instead of Voronoi, there were so many Voronoids in the architecture schools that they called Voronoi. They call it like this, you know, it means that it's like boring, you know. When you see like Voronoi architecture, you have a lot of examples of people working with Voronoi diagrams for facades, for all those elements are generated with Voronoi diagrams. Okay, because it had like at the end it's like a shell shape, no? So architects seem that they're interested into this, and many of them generated those type of patterns. You can find it everywhere. Floor plans, facades, ceilings, walls, I don't know, shapes of buildings. Okay, even for cities. A lot of time you can see urban development done mostly in the schools of architecture doing with Voronoids. Okay. So let's gonna start using the Voronoi 3D diagram. For this, what is needed? You need list of points and you need boxes. Okay. So let's going to generate a list of points out of these buildings, and also let's going to provide the boxes. Okay, boxes, we already have it. Is this geometry directly? Okay, those 3 buildings that we have. The points, the points we can we can generate any points that we want. The only, let's say, limit that we have is that those points need to be inside those boxes. Okay. So for this, double click, populate. When you want to generate points, just points inside something, you use populate. You can use populate 3D, populate 2D for a plane. You have also populate geometry. I'm going to use populate 3D. Okay. And with populate 3D, you only need two inputs. R is the region where you want to apply, where you want to extract the points. N is the number of points. In this case, we have 100 here. We can reduce it. Random seed. Again, this is you remember it's a random item. We are generating just points inside something. So seed is the configuration of this engine. An optional pre-existing population of points. You don't want to duplicate points if you already have it, okay? If you already have points inside. So the regions are our boxes. And then, well, it's already working. But let's going to reduce a bit this number, okay? Let's going to do 0 smaller than 100, okay? To have a number slider that go from 0 to 100. You remember how to do number sliders, right, guys? Sometimes for me happens when I stay a lot of time without working with Grasshopper, it's a bit hard to come back. But we can do it. Let's gonna put 40, for example, okay, to reduce a bit the amount of points. What do we have from here? I'm gonna connect a panel out of this component. So what we have out of here should be 3 trees, yes, 0, 1, 0, 0, 0, 1, and 0, 2, where on every branch of my tree, I have 40 items. I have 40 points. Okay, I'm gonna connect the param viewer, sorry, double click param viewer here to have a look of those points. Here we go. I'm going to simplify a bit. This thing is not needed, but I want to simplify. I usually like to simplify things, and especially in Grasshopper. 0, 1, 2, I prefer this data structure, easier than before. Yep. So now this list of points, I'm going to connect it into my Voronoi 3D. And then where I have is a subdivision of volumes. Okay. Understood, guys? Till here, all good? It's easy, no? This part, just generating the Voronoi. Okay, good. What we are going to do now out of this Voronoi is I am interested only in the geometries inside this. I'm not interested in the outside box of my building. I just want the inside of my building. Okay, for example, this is one cell. I think that out of here, what do I have? What is the output? Cells, boundaries. For example, I'm going to bake the cells just for you to see it. You don't have to do this, okay? Bake. I don't know. I'm gonna put it here. You see, now my buildings are subdivided into different cells. I have this one. Well, I still have the volume. I'm going to hide it. I have this cell. I have this cell. Okay, so I have different cells. So what I want to have at the end is cells which are like this. I only want the inside of my building. I'm going to divide my building into those elements. And the way to, oops, I have geometry here. Sorry. I don't know. Where does it come this then? I'm going to delete it. I'm going to delete this one. But I'm going to come back. Okay. Back. after baking. Yes. Okay. So how to get this geometry? One second, how I did this one. Sometimes now definitions are getting more complex and I have to remember the steps. So I'm going to deconstruct those cells. Okay, so deconstruct brep. Okay. I'm going to deconstruct those faces, those elements. I'm going to do with this one, and I'm going to delete this geometry. And when I deconstruct those elements, what I have are the faces of each one of those cells. Okay, I'm going to simplify here the output. Also here. Here, simplification is not going to make a huge change, okay? Let me explain you what we are doing here. Param viewer, for you to understand the data structure. Here I have 3 buildings. I have points inside the buildings. Out of here, out of the Voronoi 3D, I have 3 buildings still, 0, 1, and 2. I don't know why. I think that I could delete one of these branches because what I want are all the cells in one branch, but we can, it's not very important right now. We can leave it like this, okay? So out of here, what I will have is for each one of them are divided into different faces. Those are the faces. Okay, well, I have some of them with 0 faces. Let's see why. I'm going to extract the star faces out of here. Okay, and let's see what we have. Okay. This is good, no problem. Let's going to delete this. Let's going to continue and let's see at the end if the definition is working. Okay, so out of here, I should have viewer again, sorry. Out of the surface or the deconstruct rep, I have 1, 2, 0, 1, and 2. You see the one on the left? I still have my 3 buildings structure, but those 2 digits are a bit confusing to me, to be honest. I think that will be better to work with a data structure where we only have 2. 0, 1. So let's go to print the 3. Print 3 here, okay? With a depth of 1. And we come back to this one, 9 branches. Okay, this is better. Okay, 0, 0, 0, 1, 0, 2, 1, 2. Okay, so we have 3 branches per building. Okay, guys? Understood till here? It's okay. You just follow me. Later we analyze a bit the stuff, okay? Good. So we have the tree. Here we go. 9 branches. This is an important thing that all of us should have. Okay. The problem is that when I generate the voxel, this cell, for example, this cell that I have here, all the faces that are touching another cell are going to be duplicated. Okay, we are going to have faces that are duplicated. So we need to remove those duplicate surfaces. Okay, this is what I'm going to do in the next step. Remove duplicate faces of the Voronoi cells. Okay. For this, to remove duplicate elements, there is one component in Grasshopper that is called, and you always do the same procedure. you use cool duplicates, okay? Okay. And here comes a new thing. Sometimes your operating components have options. Options are the way that component works, okay? Cool duplicates, you can delete, for example, you have different options, no? If you do right mouse button in the center, you can click on cool all, average, merge all coincident points into one. Cool all coincident points, leave one. Cool all coincident points except one. You can remove all duplicate elements, leave one element, or merge them, okay? We are gonna click on leave one, okay? This is the option that we want. But we are cooling points, not surfaces. The thing is, out of these cool duplicates, we have indexes, index map of cooled points. And later, I can use cool index, okay? Because if I know the index of the element that I want to cool, I want to delete, and I have those elements that they are coming from here, that will be deleted, okay? The only thing that I need to do is the input of this component are points. So I need to calculate the points of the areas of those elements, okay? So area, I calculate the points of each one of the faces, of the centers of the faces that are part of each one of the cells, okay? And I connect these points here, okay? Here we go. Okay. Is it working for you also, guys? Yes? Good. When we are removing duplicate faces, let me 1 second. When we are removing duplicate faces, we also delete the outside ones. Okay, the ones that are located in the outside of those cells, because those points are inside the exterior surface. And as you can see, the Voronoi diagram, the way it works, it also generates a face in the outside, okay? Not only the cell. So when I do the duplicate, this is the trick, I delete those faces that are placed in the outside of my geometry, and I only keep the ones which are inside, okay? Generating this type of structures. The first year of this course, let me 1 second. I'm gonna try to use this thing for zooming. Yeah, way better. Okay. The first year of this course, the student had to do a model with the building that they select, and some students did a model out of this. It was super cool. It was really nice. Good. So now, guys, what we should 1 second. What we should do is let's going to put this one here. Let's going to be sure that all of them are surfaces, but let me 1 second, because I would like to know. Let's going to be sure that all of them are surfaces. Here we go. Okay, and let's going to use right mouse button, simplify. Okay, to simplify again the data structure. Let's going to see what is the data structure that we have. Okay, yeah, that's good. Again, the same as before, no? We have 3 buildings, 0, 1, and 2. In this example, it's not so important, the data structure, because later we are going to explode everything and just work with the surfaces, but just to be sure that we are being consistent with the data provided, okay? And we are generating this type of structures, okay? You can see here, right? If you can reduce the number of points that you're generating, so then you will have less cells. You will have less cells, and then, of course, the output will be only this. Or you can increase the density, generate more spaces inside your building, so then your structure will be more complex. You will have more cells inside your volume, okay? Good. Let me proceed here. So let's going to continue. Now, what we are going to do is super simple. We have achieved the most complex part, actually, of the definition. Now, what we are going to do is just, here we like to ask you, how can we do it? I would like to delete some of these surfaces based on attractor points. So let me 1 second. Let's going to organize this a bit. And here I'm gonna include exterior faces will be deleted since they are also duplicated. Well, okay. I'm gonna include this thing here, Control G. And this is for the entire definition of the Voronoi. I'm gonna place it here. Okay, so blah, 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 blah. First attractor point, second attractor. So we are going to work with 2 attractor points now. Let's gonna place an attractor point, 1 point, whatever you want, but I mean, has to be close, no? Set 1 point. We place a point, for example, here. Remember, when you place a point, if you don't have coordinates here, there are multiple ways to place a point. In Rhino, you can click on point, coordinate, or curve. I always click on coordinate, okay? And I place it here. Okay, so I have here my point that I'm going to use to calculate distances with my surfaces, okay? The approaches are, I mean, we are doing just this attractor point procedure, which is really very common in architecture, okay? So now, can somebody guess what I'm going to do? How to calculate distance from here to here? With the centers, right? With the centers of each one of those surfaces. So I'm going to use the area component. I'm going to calculate the center of each one of those surfaces. And by the way, guys, sorry, but I realized right now, I have an error here. Exterior faces is not that they are duplicated, will not be included because they are not duplicated. Sorry. Why? It was my fault, sorry. Why don't we have here the exterior faces out of the cool duplicates component when we do this? Why? Because the cool duplicates find only duplicate elements. What are the duplicate elements in the cells of a Voronoi? The faces that are common for 2 cells. Okay, The faces that are common for two cells in the boronoid in a 3D boronoid diagram means that are only interior faces. That's why this is working. Okay, sorry, because I was thinking that I thought that I explained it incorrectly, and yeah, it was incorrect. Deeply sorry, but it works because it's like this. Exterior faces will not be included because they are not duplicated. Okay, not because they are duplicated. Okay, it's the opposite. Okay, if there is any question, please stop me and tell me, Javi, I don't understand this. Okay, I have no problem explaining whatever. Okay. Santa Grasshopper is like this is a bit tough. Okay, so we have our areas of each one of those faces, okay, and my attractor point. Okay, so what I'm going to do is just calculate the distance between my point and this list of points, okay? And then I am gonna follow a different approach. Because what we did before is saying, okay, I calculate the distances, and distances are numbers, right? And then what I did in the previous classes, you can check it, it was like, okay, now these numbers are smaller than whatever number, and then I filter with a cool, I have the booleans here, I receive booleans, and then I filter those points, those faces, sorry, with those booleans, okay, saying that this number is smaller than whatever number we want. Okay, we connect this one here, we connect a number here, I don't know, 0 is smaller than 100, we connect a number here, and then we check, and then we do cool pattern. You remember, this is what we have done, and we cool these surfaces with this pattern, and we have some cooling elements, okay? We have cool our surfaces. For this time, what I'm going to do is approach a bit different, which is I am going to sort this list, but for this, I'm going to directly flatten those surfaces. If I flatten, what happens is that out of here, I will have no tree, right? I kill the tree with tree. So now I only have 1099 surfaces. Okay. Why I do this? Because now what I'm going to do, guys, is saying, okay, so I am going to sort. I'm going to sort the this list. Okay, I'm going to sort this distance because this is a number, can be sorted, and I'm going to sort synchronously my list of surfaces. Okay, so I have now out of A, what I have is my list of surfaces ordered according to the distance of my attractor point. Closest ones are the initial ones in the list, and the ones that are located farther away are the last ones in the list. Okay, for what? Because now what I'm going to do is say, okay, following this, my ordered list, I'm going to do a cool index, okay? And out of this list, I want to cool some series of indexes. What I have to provide here now is a list of numbers. It doesn't work. I mean, indexes is expecting the cooling indices that I want to delete. Okay. So we're expecting a list of numbers, 0, 1, 2, 3, 4, if you are following this pattern. What I want to have, guys, is a list of integers where I can select in order how many do I want to provide, okay? If I want 5, I want a list that they start from 0 and end at 5. I mean, in this case, I will want 6, okay? How can I do this? How can I get this list of numbers? 0, 1, 2, 5. Imagine that I want to say, no, I want 20 numbers, no? So I have a list that starts from 0 and finish at 19. How can I do this? Somebody guess? Somebody guess, guys? We saw two ways of creating lists of numbers. Okay. One of them was with series component, no? Series component is here under tree sequence series. Okay, you have also range here. Okay, you can also use range to create a series of numbers. We have those two, range and series. Okay. With series, I create a set of numbers that starts at whatever number I want. The distance between each successive number can be defined also. In this case, it's going to be 1. And the count is the total amount that I want. In this case, 10, 1 for the step, and I start with 0. What comes out of here is a list that starts at 0 and then gives me 9 numbers in this case, because I'm providing here 10. So I'm going to introduce here a number slider. 0 is smaller than 50, okay? 14, for example. And then I can select how many numbers do I want in my list. What I'm doing here is I'm going to delete faces, the 20 faces that are closer, the closer 20 faces to my geometry, to my attractor point, okay? Okay, so let's see. What is my attractor point? My attractor point is here. Let me, 1 second, if I can zoom in a bit. Okay, I'm deleting 2020, seems that it's not making any effect. So I will have to delete more. All the 20 faces, 1 second, are located just in one. I'm going to put it like here, my attractor point in the center. Sorry, the zoom is going really bad. Zoom. Okay, here we go. So you see, I'm going to increase this count. 0 is smaller than 600. Okay. So now let's see. You see, I am deleting the 2079 faces that are closer to my attractor point. So it's super difficult for me to zoom in here. Don't know why, to be honest. Okay. You see, guys? If I move the attractor point, I'm deleting more faces in other part. We can do it like this. Okay, that if I flatten the list here, what I'm doing is if I flatten the list, I'm deleting overall the 20 closest surfaces. Doesn't matter if they're in one building or in another one. If I don't flatten here and I work a bit with the data structure, that is what I am going to do now, this number, instead of being global, is going to be individual for each building. So I will delete 27, the 27 faces closer to my attractor point. Let's going to do it like this, and let's going to see the result. And we select the one that we like the most, okay? Instead of flattening here, I'm going to remove the flatten, but I want also to have just 3 branches, 1 per building, okay? If I want to have 3 branches, what should I do? Because now this is my data structure. Param viewer. 0, 1, 2. Okay, this is what I want to have. How can I do it? Because I have 9 branches. I want to delete, for example, this one. I want to delete this index of the data structure. I'm having only 1 index in my data structure. How can I do it? Somebody know?
I think with trim tree.
With trim tree, super. That's it, Nelly. Thank you very much. So we go and we use trim tree. Okay. And then we have 3 branches per building. This will be the biggest. And then this is the medium one and the smallest one. Okay. Good, good. So now using this, I'm going to reconnect all the stuff here. And then this one here. And let's see what we have. I'm calculating the points. Then, okay. So then if I select, let me see. No. Okay. My tractor point is here, no? I am going to delete 27 for each one of the faces. Okay, because here I have 400, 371 faces, 328, and out of here, you see, all of them are reduced, 27. I can increase it, and then I am deleting faces per building. I think that this one is better because you have a better control of what is happening. Doesn't matter right now. Every time I will delete pieces for every building. Okay, you see? Okay, guys, if I reduce it, I reduce less pieces per building, but still I will be deleting elements. Okay, let me see if I can do it like this. You see, guys? Sometimes things like this happen because you have a very tiny face. I mean, this one, when you bake it, remove it manually. Okay, also you can put a filter here with areas that you only want areas that are bigger than certain distance, a certain area. But I mean, I think that doesn't make a lot of sense. Okay, let me 1 second, because this one, for example, if I put it like here, okay, you see, I can delete more, less pieces, as you like. This is for the, I think that this one is better, no? At least looks a bit better than the one before. I'm going to keep it like this. And then this is the first reduction strategy with an attractor point. Okay, all this group. Control G, and then I create the group. Okay, and if you want, we can create another one with another attractor point. Okay, you can directly copy this thing. Okay, and connect what comes out of the. I'm going to simplify, by the way, the cool index. What comes out of the cool index, you can connect on the area, and you can connect also on the short list, and then you have a second attractor point that is deleting also your surfaces. So now you have two attractor points that are working at the same time, one and another one. Okay, so you can delete pieces with both of them. You can leave it only with one attractor point. You can use two attractor points. You can use three attractor points if you want and you feel that is more interesting. I don't know. This is up to you, okay? But this is just an strategy for the of how to work with the geometry. Okay, here for example, I can reduce it and delete a bit less points, and maybe with this one I can keep on deleting more pieces. Okay, cool guys. This is called okay, this is one of them. Okay, let me do something that maybe helps you to display your output, okay, and for you to understand what you are doing. Instead of selecting, what I'm going to do is I'm going to use one component that is called custom, double click, custom preview. Okay. With custom preview, I can display geometry from Grasshopper with the color that I want. Okay. I can select, for example, color swatch, this one. Okay. And click here in the color, and you can select whatever color you want. I'm going to put a red one, for example. I put it in the material. And then I can select this geometry and put it here. Okay. You will see for what I'm doing this. And also, just to understand the initial boundary where we come from, I'm going to use a VREP wireframe. Okay. And I am going to connect from this VREP wireframe my initial geometry, my base building. Okay. So check it, because now if I do a preview boundary, clicking on the blue button, only this, okay? I can display, or I'm going to change the color from this one to, I don't know, another one, this one. You can display very accurately your, how the geometry is going to look like at the end. You see? Because we are always working with the Grasshopper preview, and it's true that when, you know, guys, when you are working with so complex geometry like this one, because this is generating a lot of faces, okay? It's good to use these tools, okay? This custom preview component, okay? And then it's a matter of selecting your points and start working with them, okay? A little bit. I'm going to increase, for example, here the number of elements. You see, I can delete all of them if I want. Or, for example, my building could be something like this. Okay, I know that this is a bit, for a building, is a bit unconventional, let's say, but it's also, I wanted to show you the Voronoi because it's a feature that you're gonna find in a lot of places, lot of places. Okay, as I said, the Voronoi diagram. You can dive a bit into the concept of the Voronoi and read about it. Wikipedia, as I told you, is the best place where you can find information about it. Also, I don't know. I know that you use AI. By the way, we start with AI next week. I know that you use AI. So for example, ChatGPT or Gemini can help you also with, you know, expanding a bit the knowledge about it. But yeah, understood? Everyone here with me? It's okay? Were you able to complete this Voronoi geometry? It's another geometry that you can select for the final submission. if somebody has problems with the surfaces, you can go for with the surfaces, I mean with what we did last class, okay? With this one.
Can you maybe show the end of the definition again?
Yeah, give me 1 second because this is not getting up. Okay, so if you have problem with this, what we did last time, we can go for the Voronoi. It's simpler than this one because as you can see, we have solved it. It's way easier. But the end of the definition, Leona, is this one? Is this part or this one? It's just I use two reduction processes. Opa. It's okay like this? Leona?
I'm just wondering, my wireframe is the green, not red like yours, and I don't
Did you
really
put
get
the wireframe has to be red because I didn't change the color. But the custom preview is the one that it depends on the color that I put here on the color swatch.
Okay, then it's fine.
It's fine, no? Let me 1 second. You have to do like this, Leona. You have to, opa, yep, only those two components are the one that I want to display. So your wireframe, if you don't select the wireframe, if you don't select it, should be red because this is the default display in Grasshopper. Other thing is that you have under display the preview settings, you have modified the selected geometry and here is red, but I don't think so. If you don't touch this, by default, this is red and this is green. The selected is green and the normal is red. This is the common behavior of Grasshopper. Okay, guys. Let me put this in a white color, the Voronoi. Color. I'm gonna put it in white. This is white. I think so. Okay, yeah. Voronoi definition done. Okay, Leona, clear? Could you see
Yeah,
it?
I think it's fine. Yeah.
Okay, okay. For the rest also, can we jump into the next exercise? Voxels is called. Voxels, guys, you know Minecraft? Yes? Cool, thank you, Lander. Do you know Minecraft, right? Minecraft. Minecraft is basically a voxel game where every geometry is discretized into small cubes. Okay, so whatever geometry you have is discretized into very simple geometry, which is a cube, and display as it is. The most interesting feature that Minecraft offers is that this game can run very easily on every single platform. Okay, you can play Minecraft on your mobile phone, on a tablet, on a lot of devices that doesn't have a lot of RAM memory. You can use Minecraft there and play Minecraft very easily and without interruptions. Okay, that was one of the best features of this game and why this game became so famous. I don't know if you are you still playing Minecraft? I don't know. I stopped playing video games really long time ago. But yeah, this was one of the features of Minecraft. And when we want in computer science to display complex geometry, instead of doing like Rhino will be the opposite, no? Instead of doing like Rhino, like we display curves using NURBS topology, we can do it also as a Minecraft version with voxels. We call these small cubes voxels, and then optimize the way your computer reads this geometry. Don't take me wrong, we are not going to do proper voxels, okay? What we are going to do is just divide into cubes this geometry that you have produced till now, and then display it as voxels and play with those voxels, okay? Instead of working by layers or by floors, we are going to work more in a 3D environment, like the Voronoi 3D. Okay, here we were working a 3D. We develop a 3D algorithm, and now it's going to be the same. Okay, one thing for the base building class for this one, for the Voronoi 3D process, we only can work with geometry that haven't been modified. Okay, with geometry that is straight, that comes from the base buildings. Why? Because when in this definition we use the populate 3D, what it does is creates a bound out of your, creates like a bounding box of your geometry, and then find the points. If suddenly your box is shifted, for example, you remember that we did one definition that was like shifted, like this one, okay? This will not work, okay? Let me show you. Even, I mean, this is also, I mean, I'm gonna put this one here, just for you to show you, okay? I'm gonna connect it here. Even, first of all, this has to be flattened, always flattened. So just in case, I'm gonna put here a flatten. But even like this, you see what happens, right? The points are generated based on a bounding box. So the bounding box of this building is a bounding box which is like this. So you will have points here out of the geometry, and then the Voronoi is not going to work. You see, the Voronoi will be also bigger than your building. Okay, it's a restriction that you have. You can make it work with geometry that is deformed also, but this will be way more complex. Okay, so let's go to just use the buildings without any deformation for this definition. I'm going to come back to my class 3, and no, it's this one. I'm sorry, it's class, yeah, it's class 3, yeah, 1, 2, 3, yes, class 3, and I'm going to connect again this one with this one, okay, which is where I have my definition. Let's go to do the voxels. So for the voxels, for this one, is going to work with any geometry that we are applying a deformation. For example, I'm going to work with the shifted one, okay? With the shear angle geometry, with the modification 1.4. This will work with shear angle, but contours, I'm going to delete this one, but will not with this one. I think that will work also, but not with the rotation. Let's gonna start with the shift, with the shear angle solution. So I'm going to create again geometry component, the same as before, okay? Since I am bringing geometry from a previous class to another one, I'm going to connect this one here, called modification 1.4 shear angle geometry. Okay. And then I'm going to connect this one here and this one there. and bring it here. Okay. Right mouse button, wire display, hidden. Okay, so we don't display the wire in my geometry. Good. So let's gonna start creating our voxels. So for this, first of all, this is coming as a tree. As a tree. You see, branch 1, 2, 3. Since we are going to work in a 3D context, we don't need this tree. Let's go to simplify things, right mouse button, flatten. Okay, if I flatten, I kill the tree and I come back to the list. Okay, please guys, you are very quiet today. If there is anyone with questions or something that you don't understand, let me know. Or if this is very complex, tell me, Javi, this is very complex and I don't understand. I go slowly, or I just to explain another way, or, okay, I know that Grasshopper sometimes is a bit tough, and honestly, it's a challenge to teach this course. And I want you to understand what we are doing. Okay, this is the most important thing for me. So we have the 3 buildings here. Okay. To create our voxels, we are going to deconstruct those buildings and select the bottom and top faces. Okay, again, to find, we're going to select the top and bottom faces to find an extrusion vector that we are going to use with a subdivision of the bottom face. We're going to divide the bottom face into small cubes. We did this already with the gradient building example of VR Kingles, and then extrude those small elements into this extrusion vector. And that's all. Okay. And later we do again this removing process of reduction process or reduction strategies, okay, with our geometries. So I'm going to do a deconstruct vrep. Okay. Somebody guess, guys, how can I find the top and bottom faces? Somebody guess. Nelly, come on, you're on fire. You already answered correctly one question, not the second one. No one. Ah, come on, guys.
I would guess maybe with the area.
Yeah, that's it. With the area, if I want to sort things, I need numbers. So what is a number? Area, a coordinate, for example. Area. Good, good. Area connected to faces, right? Here we go. Faces, area. What is giving me area? The area of each one of the faces and the centroids, okay? And the centroids. With the centroids, I can deconstruct those centroids, right? I can deconstruct the points. And for each one of the points, I want the set coordinate because I want the one located in the top and the one located in the bottom. Since we are finding top and bottom faces, this is easy, no? So then, but how to find the top and bottom? Because sometimes, I mean, you see, now it's a bit messy. I mean, I have 11. Hey, wait a second. Why do I have? Close vrep, deconstruct. I have 6 faces. That's correct. I calculate the area of each one of the faces. That's correct. Usually with the deconstruct, usually the first one is the, sorry. You see? It's done in the other way around. Now it's completely messy because the top one is 52, is located in the 4th, and the bottom is the 5th one. So now didn't work as before. You see why I told you that we need to order things, that we cannot say I want to select the first one and the last one, because in this case will not work. Okay. So now guys, what I have to do for each one of those points, I have to select the top, which is the 4th one, and the bottom, which is the 5th one. But I'm going to sort them sort these coordinates, which is a number, and sort synchronously those faces. Okay, then I have the numbers sorted. The first one is always the first one. Then the rest, I don't care. They are in the same coordinate since they are the rest of the faces of the building. And then we have the top one. Okay, so I sort them, and here I select with list item the first one, which is the number 0, and the last one, which, remember, this is the trick, always is -1. Okay, here we go. So I have the first one and the last one. Okay, for every one of the buildings. They are rotated and they are also shifted. Both the formations are applied here. Okay. Good. So now, this is let's gonna start ordering definition. Deconstruct and find top/bottom faces. Good. Now let's going to do define the extrusion vector. Okay, this is going to be my extrusion vector. So my extrusion vector is going to be a line that is going from the bottom to the top. Okay, so I do a line component that goes from A to B. Okay, this is my extrusion vector. Good, guys? And I already have the extrusion vector. And now let's going to subdivide the base. To subdivide the base, we are going to use the same process that we did with the Villar Kingles example. Okay, so we get the base, the number 0, and we are going to use the isotrim component. Isotrim is extract an isoparametric subset of a surface. Okay, sorry for the name, but the surface is this one. Okay, now what I need to do is to divide this surface in a domain that I want. So for this, we can use divide domain, and you have this component, right? Divide domain square. Here we go. Divide domain. Here we go. Okay. IUV. Okay, those are the inputs. I have a surface, and I'm going to subdivide this surface into small parts. Okay. How to do this? So the I is the surface. Okay, I is the surface. U and B are the segments that I want to use for my surface. I'm gonna use here, take care, because if you create a lot of voxels, your computer will freeze. This is not a fully voxel procedure, let's say. Okay, we are just dividing into cubes our building, but the concept is similar. Okay, 0 is smaller than I don't know, 15, or let's gonna put 20, but don't use 20. Okay, 9 by 4. I don't know. Let's check if this frees your computer or not. And then we do like this. Okay, so we have 9. Hey, wait a second. What's going on here? I have the surfaces, divide domain. 1, 2. I was like, hey, why here have so many divisions and why here have not so many? They are like way different, right? Yeah, because it's always 9 by 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. And here happened the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 4. Okay. The thing is that here 4 are oriented in the long distance because of the rotation. Nothing else. Okay, because of the rotation of this building. But it's okay. This is what we are trying to do. Let me 1 second, because since this if I rotate a bit this building, this will change. Oh, but this changed the entire now. This, now the building is changed and the subdivisions have changed also. You can control these subdivisions. Let's going to keep it simple. Okay, let's going to keep it as it is. I don't want to go into more complexity. So yeah, we have this subdivision here. Okay, done. We have done the subdivision of the surface. Okay. Usually you want to avoid these problems. Let me go back. If you divide the number, for example, another way to avoid this, no? Instead of 4 by 9, you increase this number. You can do a 9 by 9 or always provide the same subdivision here. And yeah, modifying this will solve the issue. Okay, I'm going to leave it like this without the rotation in Rhino. Okay, if I rotate it, I solve it. But I want to just going to keep it like this. Subdivision of the surface. Okay, here I have it. And the extrusion lines. Okay, we have both of them. So now we are ready to generate our boxes. What would we have to do, guys? We need to divide this curve into steps that we can also let's say parameterize. How many steps do we want in our building? How many floor plans or how many divisions? This is a 3D. This is more like a conceptual design of a building. It's not so much like a proper floor plan division. You can do it like this. And then divide this curve and calculate each vector. So I am going to extrude these elements according to this division, okay, that we have. To do this, let's gonna calculate first the vector. Calculate the vector for extrusion. Okay. There is one component in Rhino where I can divide the curve. I can use the component divide curve. Different. Okay. I can put these lines here and introduce a number here to divide this curve into segments. So I can say 0 is smaller than, I don't know, 30. No idea, guys. For example, 11. Okay, 11 divisions of this curve. Or I can divide that curve also by length. You have multiple approaches. Okay, I'm going to use this one, the divide curve by number. So I can select more floor plans, less floor plans, or less subdivisions of my building. Okay, good. Now that I have subdivided this element, the output of P will be, 1 second, param viewer. I hope to have a tree. Now the data structure here is important. I'm going to simplify this. I have a tree with 3 branches, 1 per building, where I have the points here. What I want to do now is I'm going to draw using this tool. Since I have here my subdivision of elements, this is my first vector. Okay, this will be the first extrusion. Okay, then I want to calculate, I want to move this thing into this position and do a second extrusion. It's not exactly like this, but it's going to work like this, okay? Then what I want to do is do like this, move to the third one, and calculate the next extrusion, and so on and so forth, okay? For every floor plan. Okay, guys? So the way to do this is I am going to select with a list item the first point of my curve. The first point is always, in this case, we don't need to order them. This always works the same. Always the first one is the one located in the base. You see? Always. And this is going to work always like this. So I'm going to select the first point. Okay, with a list item, I index 0, I select the first point for each building. Okay? And then what I do is I'm going to calculate a vector to point. Okay? That is going from A to B. Okay? From the first one to the second one. Okay, guys? This is the moving vector. What I'm doing now, this vector that I'm calculating here is the one that I'm going to use to move my, my floor plan on every level, let's say. Okay? This is calculate the moving vector. Okay? This is the moving vector. It's not the same as the extrusion one. Okay? Moving vector. The thing is, with the last one, I am going to delete the last one, because with the last one, with the, oh my, I took the longest one to explain it. With the last one, guys, here I don't want to move my floor plan because this is the top of my building. Here is the roof, and this roof will be achieved with the extrusion of the floor plan located in the floor plan below. Okay, so I don't want this vector. Okay. So what I'm going to do is I'm going to just cool index the last vector, which the index is the -1. -1. I did it with a panel, okay? Double click, double slash, -1, enter, and then connect it here. It's a fast way just to delete the item. Okay, so I have here the moving vector. This is my moving vector. Good. Now, what I'm going to do is calculate the extrusion vector. Okay. For the extrusion vector, since I have this line that I have subdivided, what I'm going to do is divide this line into these segments. This is going to be one segment, another one, okay? And since I have moved my floor plan in each one of those segments, for example, here, I am going to use this floor plan with this extrusion vector. Okay? So the extrusion vector will be a division of this curve using those points. For this, there is one component that is called shatter. Okay? where you shatter a curve into segments. Okay, you have here your curve, and the segments come out of this t parameter. You see that this t is parameter values at division points, so this t comes from here. Okay, so here I have the same. I have curves, but on each curve is divided into small curves that I'm going to use for the extrusion. Okay. One second, let me show you the data structure. Param viewer. Here we go. 3 branches, 0, 1, and 2. Okay, 3 buildings. I'm going to simplify. Way better, only 1 digit in my data tree. So 3 branches with 11 divisions, which are the number of points that I create, okay? And I had to calculate the extrusion vector because this is just a curve. To calculate the extrusion vector, I'm going to use a component that is called amplitude, okay? Amplitude, all the vector components are located under the vector tab. All of them are here, okay? And amplitude is a very useful component because you can generate a vector from scratch, which is what I want. The vector that I want is, this is my vector, and the amplitude is going to be the length of this curve, of each one of those small lines, okay? They will be always the same because I am dividing a curve into equal parts. This is what this component does, okay? But this will be my extrusion length, okay? And then, since it's always the same, since this is always the same, guys, I can use with just select one list item, okay? Just select one vector, list item, and let's going to extrude, for example, the base, okay? Extrude. I'm going to extrude the subdivision that I did, this one, which, by the way, the data structure is the same, right? I'm going to simplify from here also. Good, 0, 1, and 2. This is what I want. Good. And then the distance, the direction of extrusion, which comes out of here. Here we go. So here we have our first subdivision of the floor plan, okay, which you can see is the first point subdivision, okay, first point subdivision of the curve. Okay, guys?
Just one question.
Yes.
Mine is not extruding to the top, but to the bottom.
George is extruding. Who is talking? Ah, Chiara. Okay. George is extruding this. 1 second, Chiara. In this direction?
Yes, exactly.
Let's go to review together, Chiara. You have the lines are correct, right? When you select the lines that goes from top to, okay, but 1 second, very stupid question. Your line is generated from bottom to top. A is the bottom, B is the top.
No, it's the other way around.
Here you go. Okay, do it now. Let's see if it works.
Yes, it's working. Okay, thank you.
You're welcome. You're welcome. The problem is that it seems the same. I mean, the curve is the same. The problem is that the vector is the opposite. So when you try to extrude it, this vector is looking downwards. Okay. Good. So here we go. We have the extrusion here. But now what we have to do is replicate this thing that we have here in all the divisions, no? For this, there is a trick, guys. What we are going to do is the problem. Let me explain you the. Let's going to do this thing properly. Let me explain you a bit the problem. The problem is a data structure match, okay? And I am going to do a tweak to be able to work with this. The problem with the data structure that we have is those vectors, okay, are generated always from A to B. A is the bottom, and B is each one of the rest of the points, no? Good. The thing is, when out of this component, I have a list of vectors. Please pay attention, all of you now, because this is what I want you to learn from Grasshopper, you know? At the end of the day, if some of you want to continue working with Grasshopper, what you need to understand is what I'm going to explain now. All the rest of things, you can find it in any website, or there are multiple exercises there to do cool stuff, but this is the trick. Data structure again. Guys, each one of those vectors, for example, are the vectors that goes from, for example, well, how can I draw here? I'm drawing already? No. Now. This vector is the vector 0, because if you go from the same point to the same point, there is no vector for moving, right? Good. This vector, the vector, wait a second. I want to use another color, red. I like the red one because it's clear. It's better, I think. This vector, vector 1, is the vector that goes from here to there. Vector 2 is the vector that goes from here to there. Vector 3, again, no? But this is working, you know? Our concept is correct. What is not correct, guys, is the data structure. Why? Because now we have this list of vectors. But the problem is, here I have this list of boxes. I have a tree also with boxes. Let me open it like this. Let's see if I can see. I'm going to reduce the number of subdivisions, okay, so I can see the list. Something like this. Yeah, way better, way better. This is my moving vectors, and this is my items. No? The problem is, I want to move. My intention is, I want to move all of these guys, all of this geometry, which is one floor plan, with each one of the vectors that I have here, with each one of them, right? But the thing is, I want to move the index 0, or the branch number 0, with the branch number 0 vectors, the branch number 1 with the branch number 1 vectors, right? And so on and so forth. I want to do, and all of the vectors that I have here, all the boxes that I have here, I want to move them with the number 0, with the number 1, okay? To have my stacked geometry. Somebody guess, how can I do this? Somebody guess, guys? No guess. No idea? No idea. Well, that's normal. But the thing is, you tell me, I mean, could be, for example, a solution that I will think about will be, well, if I graft this guy here, and I'm going to simplify also, and I'm going to simplify, I'm going to have a list of vectors where I have one vector per branch. So all of this, the thing is, all of this will be moved with this vector. That's correct. And with this one. And with this one. Okay? That's correct, as long as this. The problem is, guys, that Grasshopper is not working like this when we have trees. Exactly like this. It's working the next way. I have all of this, and they will move with this one. And then jump into the next branch. And then jump into the next branch, which is this one here also. So all of this will be moved with this, that this is not correct, because this branch here is number 1 and is part of building number 1. Imagine that this is number 1 and this is number 0. And number 1, the vector is completely different to number 0. You know? So it's not going to work. What should I do to make it work? There is one trick here. If I am able, I am going to remove the graft out of here. If I am able to have only one item here, only one item, this is going to work. Because imagine that I have only this closed VREP. If I have this closed VREP and this is the branch number 0, this closed VREP is going to be moved with this, with this, with this. Forget all the rest that I have here, okay? Forget about it. With this, okay, with all the vectors. And then for the next branch, is going to jump into my next branch, and here I will need to do the same. I will have only one item, and then move this item with all these vectors. Okay, guys? To have only one item here, and don't make really complex calculations, we can use a trick in Grasshopper that is also available in Rhino that is called group. I can group this geometry and then take a look what I have. One item. Okay, I have one group, one item with 30 objects inside. Okay, if now I move this item with 30 objects inside, this is my geometry, and I move it using this vector, I am generating my subdivision. Okay, my subdivision of the building. The problem that I have is that then I have moved groups, not objects. Okay, it's not geometry. I cannot work with this now as it is. But what I can do is say, okay, now that I have produced the movement that I want, I can ungroup it. Okay, and then I will have back my geometry. Okay. Understood, guys? This step and this group ungroup process is super common. This is super common, and you're going to use it a lot in Grasshopper. I work a lot with groups because simplify your life a lot. There are other ways to do this, but believe me, is way more complex. Is way more complex than just grouping. Okay. Good. So this part, let's say, is to create the voxels. Create the boxes. We have almost already finished, guys. Sorry for extending a bit more the class. Create the voxels, but today, as you can see, was a bit. It's more difficult. I mean, we are going to the last part of the course, so now grasshopper definitions are a bit more difficult. Create the voxels, okay, and then finally is just the same process as we did before. Okay, so I'm going to copy paste the reduction strategy here. Control C, Control V. Here we go. And I'm going to flatten also this solution, okay? Because now I don't care about flatten or no, let's not going to flatten. Let's going to keep it as it is. I think that the solution is better like this. If I ungroup, what do I mean, let me see what I have. Param beware. With param beware, what I have is, okay, I have building number 0, building number 1, building number 2, and each building is divided like in the different subdivisions. I only want to have three branches, which is each one of the buildings with all the items, with all the volumes inside the building. So for this, as Nelly said before, trim 3. Okay. Here we go. Here we have trim my 3. This is what I want. And from here, I continue working. I use this for the geometry. I use this for the short list. And here I delete the items. You see a solution which is very similar as before. Okay. And you can, by the way, there was one guy, just a comment, on the internet that he was generating geometry. I think that you can generate your own geometry in Minecraft. I'm not a very expert. I mean, I have never played Minecraft. Well, yeah, with my little cousin, he let me watch the tablet and I was digging gold or something like this. I think that there was one guy, there was one video on YouTube. I think that one guy was generating geometry using Grasshopper. It was really complex because it was JSON files and stuff like this to import it into Minecraft. Okay, so it was a bit complicated, but it was cool. It was cool. It's a software that accepts geometry from other programs. Okay, so you can play a bit here with the attractor point, like this, for example. I think this one is kind of cool also, right? And you can delete some geometry here. You can do a second or a third reduction strategy. If you want, you can remove more items. I'm going to group this one here, actually group the string theory. I'm going to copy again this thing if you want to add 2. Okay, it's just a matter of reconnecting items here. So reconnect this one here, this one there, and then you have two process removing geometry, not only one. As you like, you can put 3, you can put 1, you can choose another one also if you want. I think that if you look at the videos, if you practice a bit, you will be able to also develop different strategies, okay, by your own. Okay, guys? Of course, now if I shift the buildings, this will shift and all these things will be recomputed. I can rotate more the buildings. There are a lot of things we can still change. And the cool thing of Grasshopper is that you don't design a building, you design a process. And this is something that you need to understand, okay? Design a process, you design the algorithm. You don't design one solution, you design multiple solutions, okay? And this is the idea. Well, so with this, we are done. No more Grasshopper for today. All clear, guys. Everything clear till here. Next week, we start with AI. I'm going to give you an intro about AI. We will review what tools are most common to be used right now in architecture. We will use the tools. So I will send you an email beginning of next week about the tools that we are going to use. Last year we used Midjourney, and I don't know, I'm still not sure where to go because every year AI is going really, really fast. And I have to review all the tools available again because there are new tools, another one that works better than the ones that are before. So I am selecting right now the tools that we are going to use in class to produce also some buildings and some images. We are going to focus mostly on images and optimization processes, evolutionary algorithms. We will talk about this in the next classes. And yes, I said, I will send you an email, okay, about the tools that we are going to use in class. I hope that they are useful for you for the studio and for the rest of your studies. Okay, guys. No questions then. I'm gonna stop recording.